During a recent World's Strongest Man competition, Rev Fast pulled a C-17 cargo plane with a mass of 77,500 kilograms. The average coefficient of friction between the plane and the other parts is estimated as 15 hundredths. If Rev Fast pulls with a force of 116,250 newtons at an angle of 5 degrees above the horizontal, what is the acceleration of the plane? Okay, step one, we're going to draw a free body diagram. Okay, so here is my plane. Ask ourselves what forces are on this. Well, the gravitational force, because the plane is on Earth's surface. He's pulling it along the ground, so we've got a gravitational force. Okay, and again, it's on Earth's surface, so it is on a surface. Therefore, we know there is a normal force perpendicular to the surface. I'm going to say this is a horizontal surface, so the normal force is going to be perpendicular to horizontal, which is vertical. Again, there is a surface, and it talks about this friction, okay? The friction between the plane and all the other parts, because it's not just going to be between the wheels and the ground, but also the other parts that are moving within the plane. So I'm going to go ahead and call it static friction, though, because the big friction is probably between the wheels and the ground. So go ahead, static friction for those rotating wheels. And then we've got this other force. It says he's pulling with a force of 116,250 newtons. That is the applied force, the force he is pulling or applying to the plane, and he's pulling at an angle, okay, 5 degrees above the horizontal. Okay, and that force we do know, and it's the applied force. Okay, so I've got my picture drawn. Next thing I want to do is write down my givens. Well, I go through this again. All right, well, he's pulling on the plane that has a mass of 77,500 kilograms. So with my givens, I'll write down the mass is 77,500 kilograms. It says the average coefficient of friction is estimated as 0.15. And again, I'm saying the biggest part is probably the wheels and the ground, so since they are rotating, we say it's static friction, and that is 0.15. And it says he pulls with a force, so that is the applied force, of 116,250 newtons at an angle of 5 degrees above the horizontal. I put the 5 degrees in the picture. What is the acceleration of the plane? So we are trying to find the acceleration of the plane. Okay, so what do we know? Well, we know the plane is accelerating, okay, because it says we're trying to find the acceleration of the plane. So if the plane is accelerating, then we know we are going to follow Newton's second law, which says the net force is equal to the mass multiplied by the acceleration. Now let's take a look at this. The plane is accelerating. He's pulling it along the ground. So it's going to be accelerating in the horizontal direction. The plane's not taking off, okay? It's just going to be moving along the ground. So the net force in the x direction is going to be equal to the mass times the acceleration. Meanwhile, in the y direction, that plane is not accelerating up or down. So it's in equilibrium in the y direction. So we're going to say that in the net force in the y direction, since the plane is not accelerating up or down, that will be equal to 0. So let's go ahead and take a look at these equations. They're both net force equations. Net force means we add up all the forces in that part. Well, in the x direction, I look in my diagram, and I find that I've got the force of static friction going to the left, so I'll make that negative. And then I've got a component of this applied force going to the right. And I'm going to call that component the parallel component because it is parallel to the direction of movement. Okay? And I don't see any other forces acting in the x direction. So let's go over to the y direction. Look at that. It says the net force in the y direction is equal to, and we need to figure out what forces are in the y direction. Well, I see the gravitational force pointing down. We say down is the negative direction, so I make that negative. plus I see the normal force going up, so I'm going to make that positive. And then the one that sometimes gets overlooked. There is a component of the applied force that is going up. That component is perpendicular to the direction of motion, so I'm going to call it the perpendicular component of the force. And that is going up, so it's going to be positive in this equation as well. They start looking at these equations. We're trying to find the acceleration. That's back over here in this equation. Okay? So if I'm going to find the acceleration, I need to know the mass. Excellent. And I need to know what this net force is. So hopefully I can find that net force down here. I don't know the force of static friction. I don't know F parallel yet. So I'll need to find those. Okay? So let's go ahead and start looking for those. All right? Well, the only equation I have for the force of static friction is equal to the coefficient of static friction multiplied by the normal force. Well, I know this, but I don't know the normal force. So let's go back over here. I need to find the normal force. Normal force is in this equation. I don't know the gravitational force, but I'm pretty sure I could find that fairly easily. And I don't know the perpendicular component. So we need to find the gravitational force, which is the mass times the gravitational field constant, and we need to find the perpendicular component. Let's go here. We have a nice equation to solve for that one. Get that one done and solve for. So the gravitational force is equal to the mass, which we wrote down on the other page was 77,500 kilograms, times the gravitational field constant, 9.81 newtons per kilogram. So the gravitational force is going to end up being 760,275 newtons. All right, so we've got this one. Okay, now we need to find the perpendicular component. Well, to find the perpendicular component, we got to go back and look at our picture. Okay, this applied force here is 116,250 newtons. I'm going to redraw just this portion on the next page. $116,250 newtons, and then that was at an angle of 5 degrees above the horizontal. So this was our F perpendicular, this is our F parallel. We're going to go ahead and solve. So I see that I'm looking for this side, which is opposite the 5 degrees, and I was given the hypotenuse. So I'm going to use the trig function sine. The sine of 5 degrees is equal to the opposite, the perpendicular component, over the hypotenuse, 116,250. Multiply both sides by 116,250, and our perpendicular component is 10,131 and 9/10 newtons. Okay, so now I've got the perpendicular component, the gravitational force, perpendicular, gravitational. I'm ready to solve for the normal force. So I'm going to substitute 0 in here. 0 is equal to the gravitational force. And again, we make it negative because it's pointing downwards, so negative 760,275 plus the normal force plus the perpendicular component, which we found was 10,131 and 9/10 newtons. Combine these, move them over, and we're going to find the normal force is equal to 750,143 and 1/10 Newton. Now we've got our normal force, which we've got on the other page, which is one of the things we want to find. The normal force. We have that for later. Alright, so now we've got the normal force, we've got the coefficient of static friction, we can find the force of static friction. So the force of static friction is equal to the coefficient of static friction, which is 0.15, multiplied by the normal force, which we just found was 750,143.1 newtons. So 750,143 and 1/10 newtons. Multiply those together, we get the force of static friction is 112,521 and 45 newtons. Now we're trying to find the acceleration. Okay? We know this. We need to know F parallel. Okay? Now we know the mass, we know this. We just need one more thing to know. So we need to know the parallel component. Let's go back over here. Let's look at this parallel component. Well, this side is the adjacent side to the 5 degrees, and we've got the hypotenuse. So I'm going to use the hypotenuse and the adjacent, so cosine. So the cosine of 5 is equal to the parallel side over the hypotenuse, 116,250. Multiply both sides, we find the parallel component is equal to 115,807 and 6/10 newtons. And now I can substitute that in on the other page. We know this. Okay, so substitute that in here. So I have mass times acceleration equals the static friction plus the parallel component. The mass is 77,500 kilograms. Acceleration is what we're trying to find. The force of static friction is what we found, 112,521 and 45 newtons. And again, that was pointing to the left, so I make that negative, plus the parallel component, which we found was 115,807 and 6/10 newtons. So if we add these two together, we get 3,286 and 1/15 newtons. On the other side, we got 77,500 kilograms times the acceleration. Divide both sides by 77,500. The acceleration is 0.042 meters per second squared.